All right, so what we did last time was to look at the response of the second order system by looking at it, applying the operator in a sequence, in succession. Now, there's another way of solving these problems, which is even more general and more applicable, which is basically doing a partial fraction expansion on what we call the system operator. What is the system operator? The system operator is basically, we talked about this before, is that it's an operator. So you're talking about partial fraction expansion at PFE, and you're applying it to a system operator. In other words, if you have a system that takes an input x of t and produces the output y of t, it's the h of p that operates on the x of t to produce the y of t. So for different inputs, you can apply this operator and find it. So now let's say we have a second order system that has a system operator that can be written in the following form. Let's say 1 plus p plus a and 1 times p plus b. 1 over p plus a times p plus b. Now, we saw one way to solve this problem if you had an input x of t is to apply these two operators one at a time on the inverse operators that we have already calculated on each one of them and find the response. But there's another way. We can actually reduce this. If this were real fraction, we saw that this behaved like real fractions. We could actually express this in a different form. So instead of doing it this way, we could actually say this is similar to some k1 over p plus a plus some k2 over p plus b. Right? Now, we can solve for k1 and k2. There are different ways to do this. There's a rudimentary way of doing it, which is basically by multiplying it out and solving this equation. We can do that once, just to see how it's done. Right? So if you just multiply this, so basically find the common denominator for that and say, well, okay, that's the common denominator is this essentially, p plus a times p plus b. And it's this times that, so you get k1b, and then you get k2a, and then you get k1 plus k2 times p. Right? So that's basically the sum of these two fractions. And we want to make this be equal to that, this numerator be equal to that, which basically means that k1 plus k2 should be what? Is there a p here in the numerator? So that should be 0. So k1 is equal to negative k2. And then we know this term, which is basically says now k1 b minus k1, or we can factor k1, k1 times b minus a equals 1. Therefore, k1 is going to be 1 over b minus a, which you can basically use here. So you can say it's 1 over b minus a, and you know this is negative of that, times 1 over p plus a minus 1 over p plus b. And if you solve the same problem again, for example, if you're interested in the impulse response, you can easily see that you will arrive at the same response. So if a and b are real, for example, so now let's assume that a and b are real as a special case, then the response, and let's say they're not equal. Okay? So if they're not equal and they are real, then what is the impulse response? It's this operator operating on the impulse. Right? So the impulse response, h of t, is this operator, 1 over b minus a, 1 over p plus a minus 1 over p plus b, operating on the delta of t. Now the good thing is that now instead of applying these in succession, you can apply them in parallel. You apply them twice, but they're easier calculations. Right? That's the trick, really. So when you apply them to each one of them, it's a pretty straightforward calculation. You should by now even know this, right? I mean, what is the impulse response of 1 over p plus a? If you don't know it, you can always go back to the definition. But it's the exponential e to the negative at times u of t. Because out of the, so there's a term like 1 over p e to the, for example, at delta of t in there, which basically this becomes 1. So it's 1 over p of u delta of t, which gives you the u of t, and whatever you're left with is basically the term up front. So you get u of t e to the negative at from this, and you get u of t e to the negative bt from that. So you get 1 over b minus a e to the negative at minus e to the negative bt, u of t, which is the same response that we obtained by using the applying the operators in succession. Does it make sense? But you can see that it's an easier calculation. And the ease of application of this thing actually improves significantly, increases significantly as the size of the problem increases. If you imagine you have a fifth order problem, right? If you have a fifth order problem, applying these operators in succession 5 times is not fun. I mean, you can do it, but it's a lot of work. So this was as we said, this is a rudimentary way of finding K1 and K2, right? What is a little bit less rudimentary way of doing it, or a little bit more advanced, if you will, way of doing it? Any thoughts? Or does anyone know how to do this? Okay, so a slightly better way of doing it. So is that generally, let's say you have a Q of S, a function Q of S, where S is a complex number. And then it's written in the form CS plus D over S plus A, S plus B. So it's a rational function, ratio of 2 polynomials in S. And then you're trying to write it as a partial fraction expansion. In other words, we're trying to write it as K1 over S plus A plus K2 over S plus B. So how do you go about that? Now, the first thing you need to have to be able to do these kind of things is to have a proper function. Now, proper function has a definition. Proper function means the order of the numerator is less than the order of the denominator. So, say proper fraction, I guess. Proper fraction is where the order of the numerator is smaller than the order of the denominator. So this is the order of numerator, and this is the order of the denominator. So is this the way I've written it? Is it a proper fraction or not? Is it proper? Yes, because the order of the numerator is 1, the order of the denominator is 2. Now, what if it's not a proper fraction? What do you do? Can you reduce it to a proper fraction? How can you take a, is there a procedure? Yes?
Divide and then take the remainder.
Correct. Do it long division, exactly. Do a long division and keep so you get whatever you get, and then you have the remainder divided by the denominator, plus the remainder divided by denominator. That would by definition be a proper function, because the order of the remainder is going to be less than the order of what you divided by, right? So anyway, there's a way of reducing it to a proper function. So first you have to make it a proper fraction. Once it's a proper fraction, you have this form, let's say. So how do we find K1 and K2? Of course, one way was to do this basic algebra, right? There's another way, which is a little bit nicer and easier to do actually, practically, is that if you take this function and multiply it by S plus A. So let's say you get this Q of S and you multiply it by that. What is it going to be based on this? It's going to be K1, because the S plus A cancels that. And if A and B are not equal, so this is why we are assuming A is not equal to B, then you get K2 times S plus A over S plus B. Because if they are equal, then they would cancel too. Yes?
Is it just supposed to be S plus B in the bottom? Or is it supposed to be S plus P?
S plus B, yes. Thank you. I was looking at it upside down and in a mirror. No, I wasn't. Just made a mistake. All right, thank you. So now this function evaluated. Now if you evaluate this function for S equals negative A, what do you get? Well, essentially it means that you set S to negative A. If you set S to negative A and A and B are not equal, what do you get from the second side? So you get what? What is this whole thing going to be? K1, right? So that's a way to calculate K1. You take your function, let's say, whatever, this function, you multiply it, or fraction. So let's say I want to find K1. What do? I multiply this thing by P plus A and evaluate it for P equals negative A. P is really an operator, so you replace the P with a negative A. So if I do that, this disappears. So I have to put P equals negative A in this. What do I get? 1 over B minus A, right? I get that. Now if I want to calculate K2, I multiply by P plus B and again, set the P to negative B this time. What do I get? I get negative 1 over B minus A, right? Because it's going to be B minus, A minus B, right? Which would be negative 1 over B minus A. So I can calculate K1 and K2 much faster, much easier that way. And then we'll see how it generalizes to multiple roots. But let's see an example of this. Let's do an example to see how this is applied in a circuit example. So this is one way to do the partial fraction expansion. Any questions so far? Yes?
Wouldn't if you plug in S equals negative 8 in that equation, right, it's just 0, QS equals K1 plus 0?
No. So you say the question is, when I apply this, doesn't this become 0? It doesn't become 0 because it has a denominator that's also S minus S plus A. So you have a 0 divided by 0 that you have to resolve. But those zeros are exactly equal. They're not two different kinds of zeros. They're the same zero, so they cancel. I mean, I'm speaking in funny language, but that's the essence of it, really. It's like the infinities. You can have the same infinities and different infinities, right? And there's zeros, and there's some zeros that are equal, and there are some zeros that they're both 0, but one 0 is more 0 than the other 0. Right? And there are equalities that when some are equal and then some are more equal. Yeah. Yes, you got it. Right. Okay, so here's the thing. So let's do an example. Let's do this could be a mechanical example, a circuit example, anything. Since this is more an electrical engineering class, we'll do a circuit example. So let's see. Let's just have some numerical values that kind of work out a little bit better. So let's say you have a Vs of t, and then you have a capacitor, a resistor, and an inductor. So the capacitor is 1 over 1/20th of farad, resistor is 4 ohms, and inductor is 5 henries. And then let's say our output is V of t. So we are interested in determining this voltage, and we want to know what it is for, we can determine it for different inputs. So the key part is really finding the system operator. What's a system operator? What is a system operator? What does it do? It operates on some input, some waveform of time, some function of time, and it generates another function of time. What function of time does it operate on? The input, which is what? Vs of t, right? So the system operator in this case would be operating on Vs of t to produce V of t. So the key is really what is the system operator, which is the transfer operator, really. It tells you what the transfer characteristic from this input to that output is. And then we'll see in a couple of lectures that basically it becomes the transfer. You can modify, evaluating it for a certain input, it becomes a transfer function, which is a little bit less general conceptually, but more useful practically. But right now we are dealing with a system operator. So, okay, what is that transfer function? So how do you calculate this? How would you go about doing this calculation? Well, how would you determine this voltage in terms of that voltage? If these were resistors, do you remember we just said this is like LP, this is 1 over Cp, and we can think of them as resistors. If they were 3 resistors, how would you do that? How would you do that? Right, it's a voltage divider, right, between this impedance and that impedance. So what is this impedance? This impedance is the parallel combination of these two, which is the product divided by the sum. You can write as RLP divided by 1 plus R, divided by R plus LP, right? And then divided by the sum of this impedance and that impedance, which is basically 1 over CP plus 1 over, or RLP divided by R plus LP. So this is the system operator. Now we have to simplify it a little bit. And, of course, we can multiply both numerator and denominator by R plus LP. So you get RLP here. And then in the denominator, you get and times CP also. So let's do all of that at once. CP squared. And then I get a R plus LP here. And I get R LCP squared here, right? Which I can even simplify a little bit more by dividing by R. So I can divide both sides by R. The numerator and denominator by R. You can see R, or even, let's make it even simpler. Divided by RLC. So then you get P squared divided by P squared plus 1 over RC, P plus 1 over LC. Okay? Now, let's put the numerical values in. Let's plug them in and see what we get. So if you put the numerical values in, you get P squared divided by P squared plus 1 over RC. What is RC? RC, 420. So that's 1/5. So I get 5p plus LC. L is 5 times this is 1/4, so I get 4 here. So I have to factor this, right? But before so first thing is that I have to factor it, right? I mean, I need to find what the factors are. Do we know what the factors are? What are they? 1 and 4, right? So this really can be written as, so that we know this is basically P plus 1 times P plus 4. But we have to do something else before we do that, right? There's something here that we need to fix before we can do partial fraction expansion the regular way. What is it? We have to make it turn into a proper fraction, right? So how do we do that? Well, in this case, it's pretty straightforward. The easiest way of doing this is to add and subtract what's missing from the denominator, right? So I can say P squared plus 5P plus 4 minus 5P minus 4, right? This is the same numerator still. Divided by P squared plus 5P. This is basic algebra, essentially, right? So this part is what? What's that part? 1. I did it intentionally to make it 1, right? And then I have minus 5p plus 4 over, I can now write it like this, p plus 1, p plus 4. Okay, so this is my system operator. Now, what I need to do is so I have a unity operator. What does a unity operator do? It produces the same thing, right? It just takes it from you, and it's a good banker, right? So now it's basically now we have to do partial fraction expansion on this one. So I will employ your help here to do that calculation, so we get some practice. So we think that we can write this as something, or it could be a minus or a plus, so it doesn't matter. We will find the signs later. And something over p plus 1 and something over p plus 4, right? So let's say we are doing the partial fraction expansion on this thing. Let's forget about the minus sign for a second, then we'll deal with that minus sign. So what are those two terms? What are these numerators? So let's start. Where should we start? We did second row last time. So we can maybe start from this end. Third row. Okay, so what's the first thing I need to do to calculate this coefficient? Multiply this by p plus 1, which eliminates p plus 1. So it makes the calculation easier, actually. And then set p to what? Exactly, minus 1, negative 1. So what do I get in the numerator? Negative 1. And what do I get in the denominator? 3. So I get negative 1/3, right? And I had a minus sign, so this becomes plus 1/3. And I have another negative sign I have to take care of here later on because it's this negative. So now how about the second term? Why don't you do it yourself too? So I multiply by p plus 4, this disappears. And then what happens? And then set it to minus 4. What do I get? Minus 16 over minus 3. So it's 16 over 3. And then I had the minus sign, so it becomes 16/3. I think that's correct. Yeah, okay. So that's my system operator. But now the beauty of this form is that I can apply it to anything pretty easily, right? I can use it on, let's say, if I want to know what the impulse response or the step response of the system is, or the impulse response. Let's ask the impulse response question first. If I ask you, what is the impulse response of this system? How would you calculate it? Formally, what you say is that, well, it's a system operator operating on the impulse, right? This is generally true, so if V of S is an impulse, then it should be still true. It's a special case. And what do I get? So I express it in this form. So 1 plus 1/3 over p plus 1 minus 16/3 over p plus 4. Operating on delta of t. So do I know the answer already? Do we know the answer? What is the answer? Let's go through the answer. So what's the first term? What does the first term generate? Delta of t. Okay.
And then 1/3 e to the negative t.
1/3 e to the negative 1t, which is t, u of t.
And then minus 16/3 e to the negative 4t.
Minus 16 e to the negative 4t u of t. If I can also factor u of t between these, but it's not a big deal. 1/3 between them, but it's not a big deal right now. So that's the answer. That's the impulse response. The impulse response has an impulse. So if you plot it versus t, h of t, so the h of t has an impulse, and then it also has these two time constants. One that's the 1 over t, I mean a t time, t equals one, a tau equals 1 time constant, and a tau equals 1/4 time constant. So one is faster, so there's one that has a larger amplitude that is faster, and it has a smaller one that's smaller. It's a sum of those two exponentials. So you get an impulse, and then you get something that decays at some rate, right? So you can add these functions, plot them, do whatever you need to do with them. So you know the response. You can calculate the response. Any questions? Is this clear? Now if I ask you what was the step response of this thing, right? We say, what is the step response of this thing? Well, you just apply this to the u of t. And again, it's the same ditto u of t, right? Which produces what this time? Maybe next in line. Do you remember what the response to these things are for the step? It's 1 minus exponential times u of t, right? So it basically becomes 1/3 1 minus e to the negative t u of t minus 16/3 1 minus, I'm answering it for you.
Yeah, 1 minus e to the minus square root of t.
Yeah, u of t. So that, it is what it is. I mean, so you get some response that has a step plus these things, which basically one is like this, with the smaller coefficient, and then a larger one with a slower or faster time constant. So it's the sum of these three plots. Again, it really goes back to superposition in a way, right? In a sense that you can allow break the system into parallel systems and apply them individually. So you can say, my system, what you're really saying when you're doing this, for example, in this partial fraction expansion, is that, say, instead of looking at P of t with x of t or y of t or whatever, Vs and Vt, I'm saying that this is equivalent to three simpler systems working in parallel. One is a unity system. One is that 1/3 p plus 1, and the other one is 16/3 p plus 4. And then you take all three, and then you add them up, your output. You may say, well, wait a second, you're making the system more complicated. No, you're not making it complicated. You're making it more tractable and understandable. And again, that's very important when you're trying to make things that when you design things, right? Because you want to break it into smaller elements that you can track and understand. Any questions? No? Let's do another example. Okay. And again, I'm not going to go through all the derivation details of this thing, just to show you how a circuit can be translated into something simpler. So let's say you have something like this. By the way, I should have asked you what the order of those systems are. So I didn't ask you one on that question, on that previous one. But let's do it on this one, because that would have been trivial anyway. So this is 10. So it has some values: 10/6 farad, 1/6 farad, 3/5 henries, 1 ohms. And you can show it this way, or as you become more proficient in electrical engineering, a lot of times we show them this way. So this should mean the same thing to you, right? You can have different grounds at different places. So that means that they're all connected. You don't need to explicitly connect these. We save ourselves a little bit of schematics complexity and all those things. But anyway, so if you have something like this, now you can do the evaluation. But before we do that, first of all, what is the order of the system? Show it with your fingers. Okay, raise your finger. What's the order? How many different degrees of freedom? How many different initial conditions? We went over this, right? So I have some 2s and some 3s. 2 and 3s. Okay. So raise your hand if you say this order of the system is 1. Okay. Raise your hand if you say the order of the system is 2. Raise your hand if you say the order of the system is 3. Okay. See, this is one of those places where the democracy doesn't work. A majority can make a mistake. But anyway, so why do you say it's 2? It's not correct. It's 3. But why did you say 2? Those of you who said 2, that's fine. Just I want you to articulate your reason. It's perfectly fine. Yeah.
So my thought was that it looks like we have 2 nodes.
Okay.
And, applying initial conditions across the first node and the second node would take care of all of the capacitors as well as the inductors.
So your thinking was that since we have 2 nodes, so I'm repeating it so that you have 2 nodes, and if you specify the voltage on this node and the voltage on that node, you've specified everything there is to know about the system, right? That was the logic. And I can see that that's kind of like that logic. But remember, the initial conditions are not defined for nodes. They're defined for energy storage elements. So you have to see how you can define the state of an energy storage element. How many energy storing elements do you have? Obviously 3, right? Now, the question is that can you specify 3 different initial conditions without running into a contradiction? can I make this voltage be 1 volt and this voltage be 2 volts and make this current be whatever, like 4 amps? Is there any fundamental contradiction? Do I violate KVL or KCL? Do you see any violations? No. So I can really define 3 different initial conditions. Now, if this were a capacitor, then if I define this to be 1 volt and 2 volts, then the initial condition of the capacitor is defined in terms of voltage. Then could I define this to be any arbitrary voltage I want it to be? No, right? In that case, if this were a capacitor, in fact, this would become a second order system. Now that this is an inductor, this is actually a third order system. Is it clear? You know, one thing to look for is that capacitive loops. If you have capacitive loops, solid capacitive loops that have nothing else other than a capacitor, that tells you that that by itself reduces the order of system by 1. Again, it's a rule of thumb. You have to really go back to this, but think about it, because if you have a loop of n capacitor, if you define the initial voltage on n minus 1 of them, you have defined the nth voltage, right? By, what is the one that, what's the rule that defines, or the law that tells you? KVL, right? KVL, so if you go through the loop, if you know n minus 1 of those, the nth one is known. Just need to add them up and subtract it from 0. Okay? So this has to be a third order system. So, and then again, I'm not going to go through the, I mean, you can go through the algebra. You just basically show these as LPs and 1 over LPs. I'm just going to show you what the end result is to save time a little bit here. So this is basically going to be p cubed plus 6p squared plus 11p plus 6. Now, there's one thing here that is important to think about and ponder before we go about doing this. Now, remember, the reason, why is this a useful thing? Why is this partial fraction expansion can be done? This is an important point, by the way. Just forget about this example for a second right now. Let me ask you this question. Why is it that we want to think about it this way? Can we always write these as a product of, as a sum of these like simpler fractional functions? What is it that makes it possible to do that? It would be possible if you can factor the denominator, right? Can you always factor the denominator? If I write an arbitrary nth order polynomial, can you factor it? Or, well, there are 2 different questions. Can you or I or any one of us, can we factor it? Or can it be factored? There are 2 different questions, right? The answer for me would be, once you go above 3 is no. I mean, unless there's some obvious one. And even for 3, I will struggle sometimes. I just have to know what I'm doing. The
quartic equation, it's just a couple of pages.
Yes. And you know, so this, okay, so that's a good point. So she says, yeah, when you go from third order to fourth order, the quadratic equation has like a simple formula, right? The cubic equation has a messier set of formulas that involve different things and different conditions and all those things. You reduce it to a special case then. Now, the fourth order equation is incredibly complex, right? There's a Cardano, is it a Cardano one? And once you go above fifth, you can actually prove, and Abel proved that you cannot come up with a formula. It's not that we don't know the formula. You can prove that there is no formula. So don't waste your time, essentially. Right? Yes?
So like Mathematica and whatnot, go about solving higher order polynomials.
Oh, okay. So they don't use a, so that's a good question. So it's the question is, how does mathematical or, other solvers do that? There are lots of numerical ways to do these things. Right? No, but then, okay, so yeah, I'll get there. So you can always do it numerically, right? I mean, you can always basically use their Newton method, and there are lots of other methods to find the roots of the nth order polynomial. The question I think you're asking is that how does it give me the numbers that it does, right? I mean, it just gives you really kind of factors in a certain way. It uses a combination of numerical, if you go to very high order one, it uses a combination of numerical methods to estimate where they are, and then uses that to verify Uses those results to verify the result and see if, okay, these are the roots. And for example, numerically it gets like 5.000001, right? Okay, well, let me plug in 5 and see if I can get it. Right? Yeah. Yes. So that's one thing it does. But the key part about it, key point is that in general, there's no formula. So you may say, well, this is very, very difficult. But there's also something even more powerful that says something about it. Yes?
So, I mean, you could do it with rational root theorem, and like there's some polynomials that you'll be able to kind of piece out what the rational roots are and like that, figure out what the
Sure, you can. Oh, there are all sorts of tricks, but the most important element of this thing is not. Okay, so there are two parts to this. One is that, but can it be factored? I think that's the most important question. If I give you a 10th order polynomial here, can it be factored? Yes. How do we know that? There's a theorem in math that says that. What is that theorem called? Fundamental theorem of algebra. What does fundamental theorem of algebra say? So it says if you have an nth order, well, there are different forms of it. So one form, if you have an nth order polynomial with real coefficients, the root, you can factor it in terms of product of first and second order polynomials with real roots. Right? So you can factor it as product of first and second order polynomials with real roots, or equivalently, you can factor it as product of first order polynomials with either real roots or roots that come in complex conjugate pairs. Why? Because if you had the second order, or the quadratic one, right, second order polynomials with real coefficients, the roots of that are, if they're not real, which means that if they were real, you could factor it, right, in terms of first order real. If it wasn't factorable as first order one, it means that the roots are complex. And if they are complex, they are going to be complex conjugate pairs, because there's a plus minus square root, and that's the only part that has a square root. That's the only part that can generate I or J, I guess. Right? So the point is, you can factor it. It can be, well, the point is that it can be factored. Now, and the beauty of it is that, and that's why really, if you think about it, that's why we spend so much time talking about first order and second order system, right? You remember we did the second order system in detail. We never go through the third order system. Because if you think about it, a third order can be factored as a first order and a second order, or 3 first orders with real coefficients. And if you do partial fraction expansions of those, you will end up with a first order system and a second order system. And the responses of the first order and second order response system are the only things that you will get. So what the overall response is going to be a superposition of the responses that we just talked about for a second order system, for example, or first order system. The exponentials, or exponentially decaying sinusoids and things of that sort, or exponentially growing sinusoids, or exponentials growing, or t times exponentials u of t. Those are the only kind of responses you can have from these systems. This is very powerful. It says that any kind of circuit, any mechanical system, anything, as long as it can be written in a rational form, its response will be limited to these kind of things, its natural responses. That's why we spend so much time here and in physics and math and all those things talking about exponentials and the quality factor and decaying exponentials and all those things, because that's pretty much all there is for these kind of systems. You just need to decompose it, basically, or disintegrate it into these smaller pieces, deconstruct it, right, into these little pieces, and then you know how these little pieces work, so you can put them back together and then make whatever you want. So anyway, so that's the point. Any questions? Any comments? By the way, if the coefficients of the polynomial are complex, right? The most general form of fundamental theorem of algebra is that if you start with complex coefficients, then you still can factor it as product of first order polynomials. But their roots will be complex, but do not necessarily come in complex conjugate pairs. if they are real, they always come in complex conjugate pairs, which is very important. You will see when we talk about poles and zeros. The poles of real system are, you either get one real one or you get two complex ones or pairs of complex conjugate ones. And they have a certain behavior. And that's necessary to produce real responses. All right, any questions before we go back to this example? No? All right. So this example. So does anyone know how to factor this? Do you know what the factors are? All right, wow, man, good. Okay, so let's ask in the backs. We haven't answered.
B plus 1 times B plus 2 times B
Plus 3. Okay, good. How did you know? You did it? You did? Okay, that's good. I'm impressed. It wasn't as obvious to me. These things, you know, the trick with these things is that if you construct them yourself or somebody, when they construct them, they can make them whatever they want. I mean, I can, and then, but it's given to you. So well, what do I do with this? If I just take p plus 1 plus p plus 2 plus p plus times p plus 3, p plus 4, p plus 5, multiply it out and give it to you, give you fifth order polynomial, you can scratch your head for long. I mean, I would scratch my head for a long time. I would just basically, and, or basically go to the numerical answer. The key is that even if you can't find a formula, you can always find it numerically. Right? So anyway, so that's what it is. So what do we do with this? Can you think of how do we do the partial fraction expansion? So the partial fraction expansion is going to be something over p plus 1, something over p plus 2, and something over p plus 3. Right? So what are those three things? So who's next in line, I guess? Yeah. So how do we calculate the first one? You remember the trick, right? We multiply by what? Yeah, which basically eliminates this. And then set the rest, p to what for the rest of it? Negative 1. What do we get? We get negative 1 here. We get 1. And then 2. So it's 2. So it's, what's the total number? What's the overall? So it's 6 divided by 1 times 2. 3. Yes. Now, how about this term? How do we calculate that? Okay, and get rid of that because you're multiplying with that. So what does this one give you? Negative 1. What does this give you? 1. So what do you get? Negative 6. And then for the last one, so again, eliminating this, negative 2, negative 1. I want everyone to do it in their heads as we're doing this, right? You're not off the hook yet. Okay, so what do we have? What's the total? 3, plus 3, right? Because you have two negatives. So that's basically what the partial fraction expansion is, I think. Yes. So if I ask you, what is the step response of this system, right? What is the step response, S of t? What is it using h of p? If I want to express it in terms of h of p, is h of p operating on what? On u of t. So now I have to have this h of p operating on the u of t. So I get 3 over p plus 1 minus 6 over p plus 2 plus 3 over p plus 3 times u, operating on u of t, not times. Okay? So what are these operators? Do we know the response to these operators? All right. Do I have to do this integral every time? Because I already know the tricks for these things, right? And that's where we are going with this. You will see pretty soon that we don't need to do any of these integrals eventually. That's the good news.
What's the bad news?
The bad news is that we have to learn it. It doesn't come for free. It can't. The bad news is that you can't download it yet into your head. You have to practice it to learn it. Okay, so here's the thing. So what's the response to the first one? Do you want to go to the next person? Yeah.
3 times 1 minus e to the negative t.
Exactly.
Minus 6.
Do you want to keep the u of t here, or do you want to just putting the u of t at the end?
Yeah.
Okay. So you know what? When you are doing this, not to forget, here's a piece of advice that I myself don't always follow. You know, Oscar Wilde said, people tend to give advice they don't follow. which is true. Because your mind is attracted to the things that are important that you haven't, you have the mistakes you've made and you can't probably still make. Okay. All right, so times 3. Okay, so what's the next one? Minus 6 times 1 minus e to the negative 2t. 3t. Okay, so now that I have the u of t, I can put it on the end, so it looks better. So I can simplify this a little bit, and I can factor the 3 if you really want to. So you get 3, you got 1 minus 2 plus 1. What do we get? So I get e to the negative t plus, or minus 2e to the, minus e to the negative t, minus 2e to the negative 2t plus, plus, yes, minus, thank you, e to the negative 3t u of t. Right? So that's the response. That's the step response. You say that this is not just that, it's 1/2 of that. Yeah, you're right. You're right. You're right. So what we're basically saying is that I'm integrating e to the negative 2t, right? So there's a 1/2 coefficient that comes out. That's right. So you get 6 over 2, and then it becomes 3 over 3. So what you have is 3 minus 3 plus 1, right? Which makes a whole lot more sense, actually. So there's a 1 up front. Yeah. And the reason it makes a whole lot of sense is, or a whole lot, 1 minus this. And why is it that this 1 needs to be there? It makes a whole lot of sense. You have to think about the physical system, what it does. Right? Think about this. This is it. Let me ask you this question. At very low frequencies, when things are moving very slowly, right? What does the system do? What is the relationship between the output and input? What happens to the inductors and capacitors at very low frequencies? If they're not, so what is a capacitor like if things are not changing? It's an open circuit, right? And what's an inductor if things are not changing or changing very slowly? Short circuit. So this is open, this is not there, and this is short circuit. So this voltage would be exactly the same as that voltage at low frequencies, meaning that if things don't change a long time, that's the way it should be. Now, why is that? Because if you think about it, if I have a step here, some things will happen, but after a long time, I've applied like a unity voltage here. So I have to see something at the output, right? That's of the same magnitude. Otherwise, it wouldn't be correct, because eventually the output needs to, in the long run, asymptotically needs to reach this 1. So by looking at the circuit, I can see if my answer makes sense or not. It will get there with some time constants and some things, but eventually it has to get there. So this 1 has to be there.